Tonight's meeting is being recorded.
Okay, this is a cough. This is first class in basic electricity. Remember, I always start out with a concept and then base whatever I can off of that. So my saying is concepts go in and they don't come out, especially if you sleep on them, thinking about go to sleep when you have a concept in your mind. So this is first class in electricity, and the concept is going to be water and being pumped by a pump. The pump has pressure. We have a pipe, which is going to take the flow in it. And we have this great drawing of a nozzle over here. And we have the water, another great drawing of the water going into a pan. And the pan is going to return water to this pump so the pump can keep pumping. If you don't do this, if you don't return, you won't have any water to pump. Okay, that is analogous to electricity. I always need a return for electricity. So it's a pretty simple model. If you have, so let's say the the nozzle's the same, everything, the pipe is the same, and we raise the pressure, we get more flow. A water flow, usually we would measure it in gallons per minute. Pressure would be pounds per square inch. Don't really have, I'm not going to introduce a unit for the physical resistance of the nozzle. It's like how far it would be more like how much it's open or how much back pressure it causes. But we don't need to worry about that. So if we keep the pressure the same and we open the nozzle, we'll also get more flow. Okay, we'll get more gallons per minute. So this is completely analogous to an electrical circuit, which I'm going to show you now. They both don't fit on here. Maybe I can make them. No, that was worse. Let me see. Okay, well, I can maybe switch between them. So V is the same as P, and it's in volts. I'm showing a symbol for a battery or any type of power. V in volts, we have a wire instead of the pipe. Okay, we have a resistance, which is measured in ohms instead of a nozzle. And then we have our return wire here, same as we have return water there. If we break any one of these open, we'll get no flow. Current is in amps instead of gallons per minute. And again, if you keep this resistance the same, you raise the voltage, our current is going to go up. If we keep the voltage the same and we lower this resistance, the current is going to go up. If we raise this resistance, the current's going to go down. So it's the same as opening and closing a nozzle. If you open the nozzle, the resistance goes down, and if you close the resistance, the resistance goes up. So we have a simple equation for this. Of course, in electricity, you always got to have some equations to describe everything. We can't see electricity. We can measure it. I drew a meter out here. We can measure parts of it, but most of the time we need equations to explain different things that are going to happen when we change things. So this is a very simple equation. V is equal to IR, and I always call it VER when I was memorizing it, or when I still use it. I call it VER, V-I-R. V is equal to IR. And then, of course, you can rearrange this. Multiply both sides by 1 over R. Cancel the R out on here and end up with a V over R here, and that's equal to I. So if you listen to my algebra classes, this will make sense. Now, the one thing I always say whenever I talk about equations is it's an equation. The equal sign has to be enforced. So another thing I want to say here is let's hold one thing constant. Let's hold, let's say, the R constant. Okay. I shouldn't have clicked that. Hold the R constant, but let's raise the V like I talked about with raising the pressure. So what's got to happen in order to keep that equal sign an equal sign? The I has to go up, right? So that's always an important concept with any type of science is, well, let's hold this thing constant and let's see what happens when this goes up and what you have to do in order to make that equation equal. Okay. It's called Ohm's law. A famous guy named Ohm, Henry Ohm. I'm not sure. You can look him up. He was one of the original founders of electricity. There's also another equation for power. We don't need to do much with that, but I just showed it. Power is equal to I times V, PIV. That's how I remembered it. It kind of makes sense. Power is really energy. So the more you up the voltage and the more you up the current, the more energy you're going to take from the battery, right? You know, same as like with water flow. The more you up the pressure and you lower this resistance, and you increase this flow, sorry, you'll have to have a lot more power coming out of the pump, right? So it kind of makes sense. So I did a little simple example here. If we have a 10 ohm load, call it a load, there's the symbol for ohms. Now we have a 12 volt supply, like your car battery is around 12 volts. It varies, it's not going to be exactly 12 volts. It varies depending on whether you're charging it or it's being discharged or it's just sitting there doing nothing. It varies from kind of like 9 to like 15 volts. But everybody always calls it 12 volts. I could talk more about that, but let's just say we have a 12 volt battery and we have a 10 ohm load. Then if we solve for I, 12 is equal to I times R. So we're going to divide both sides by 10 and get 12 over 10, and we're going to be left with I on the side, and that's 1.2 amps. If you want to do the power, we can multiply I times V, which we already figured out the current. So it's 1.2 times 12. Okay, so main thing is the concept of this. Just to make it more interesting, if you're running water in a pipe and you jam this off somehow, like your washing machines do, your dishwasher and your clothes washer, you'll hear like a bang if you can close this fast enough. That's because we actually have flow in the pipe and there's momentum, and I'll go into that more. And it takes force to stop momentum. Now I'll talk more about that. But current, if you were to cut this current quickly, it would actually cause a spark. So it's just something interesting. You could do this with, well, I'm not sure I should suggest this, but you could run your vacuum cleaner like in the dark and then pull the plug and you'll see a large spark. Now, that is not that safe to do because you can hurt your vacuum cleaner. You could do it once or something. It's not that. It's better to use the switch on the vacuum cleaner because it's made to handle the current. It also doesn't change it as quickly. It doesn't try to stop it as quickly. But you can see that the water model and the current model are very similar, at least as far as what I told you. All right, so I'm going to stop for now and then go on to something else next.
This meeting is being recorded.
Okay, hello, this is the second in a series of basic electricity conceptual learning. I wanted to talk a little bit about the meter I dropped on here. There's a bunch of different meters and they have a whole bunch of options. They're definitely difficult to figure out sometimes, but I wanted to go over at least some of the things about one. This is like a cheaper one. Hang on one second. Let me, can I pause? Um, so one thing is the connections. I mean, in this picture, there's two probes. They would normally be, the red one would be plugged in. I'll zoom in on this. The red one would be plugged in if you're measuring voltage. The red one would be plugged in here, even though this seems to show red. But common is usually the ground or the common point of the circuit, which would be the negative of the battery in this case. So when you see COM, that usually means the ground or the reference point. Not necessarily ground, but everything that we're referencing off of, which in this case is the negative of the battery. Okay. I didn't draw the negative there. I should have a negative in there. Okay, so then the red goes in this thing that says volt, ohm, and then milliamps. So it has multi-functions. And then in our case, if we're measuring voltage, so now we're studying DC voltage at this time, we would put it on one of these ranges here. So there's not a lot telling you that. There's off, and then we go right into voltage. See that little symbol there? Different ones use different things, but that's their symbol for DC. This is their symbol for AC. Excuse me. So in this case, for measuring DC voltage, we can go 200 millivolts, which is 0.2 volts. I mean, I throw these things around because I work with them all the time. But basically, a milli is a thousandth. And so this would be 0.2 volts. This would be 2000 millivolts, which is 2 volts because you move the decimal over 3 times. And I know I throw these around. If you go too low of a scale, so if we were measuring this circuit here where it's going to be 12 volts, and you went on one of these 200 millivolts or 2000 millivolts, you would get usually like an OL here, overload, and it'd flash at you or something, or maybe sometimes they just blink numbers. So usually it won't hurt the device. Putting way too much voltage on could hurt the device, but it looks like this guy here can go all the way up to 600 volts DC. Okay. So we would put it on the 20 volt scale, and then we would put the red to the positive and the black to the negative. You don't need to worry about which way you put the black and the red because you won't hurt the meter. What'll happen is you'll just get a minus voltage up here. If you put the red down here and the current's flowing this way through your resistor, it'll be positive here and negative here, so you'll actually read a negative. If you put the red here and the black up here, you'll just read a negative 12 volts here. Okay. So then on my next screen here, I have how you would measure current with this same meter. So current is a little more difficult to measure. You actually run the current through your meter and out. So the COM is the current coming out, and this other one, whatever it's labeled, in this case 10 amp max, is where the current goes in. Okay, and then if you wanted to measure milliamps, it would come in here and come out here. Okay, so I drew it in our little circuit there. So current is flowing in this direction, and it should show up as positive. And in this case, I'm saying, let's say we do this one here. We have 10 amps. Oh, I probably shouldn't have said that because that's the max of this thing. Probably could take a little bit more. Now, this type of thing you can hurt if you put too much current through it. But you could probably take 15 amps anyway. Now, the milliamp one may not be able to take that much. What they have a little resistor in there of some type, and the cheaper meters have a little resistor in there that they measure across. So if the resistor is too small, it'll burn up your power. Your PIV will go way up. So if we were to do that, we should get 10 here. If it was a little over 10, it might give us overload in this case. So I should probably make this, more like a 1 amp thing. So again, there's 2 ranges for the current. They still use the same common, but you go in either one of these. And if you look at current, we're not looking at AC voltage, we're not looking at DC voltage, we're not looking at ohms yet. There's another function here. We're here with the DC current again with that little symbol they show. Now we would be on the 10 volt range. We can go down all the way down to 2000 microamps, which is actually 2 milliamps, and then 20 milliamps, and then 200 milliamps. Now I realize I throw those around. Micro is 10 to the minus 6, milli is 10 to the minus 3. If you work with them all the time, you get quick with them, but I understand not being able to do that real fast. There's another function on this meter since we're here. If you put the selector to this, it'll beep when you get below a certain resistance. It's actually a continuity check. So they show the little sign, the little I don't know, audio symbol. And then it also at the same time does a diode check. We have to go over what diodes are. And then we'll go back over the meter. Also AC voltage we're not going over. Now we did talk about ohms. You can measure with this one. You can measure I don't know what this thing is. I don't, okay. Something popped up. I think I don't know if you saw it. So you can also measure ohms on this, which is 200 ohms, 2K ohms, because it's 1,000. 20K, you might not be able to see the K, 200K and 20 meg, oh, and 200 meg. So if we were measuring this resistor here, what did I say it was? 1.2 ohms. We would go on the 200 ohm range. Now, there's something important about measuring resistance. If you measure resistance while it's in circuit, your meter is not going to read at all correctly. Even if, like if you measure a resistance on a circuit board, say, and you have other circuitry hooked up, but the power is off, you'll still get parallel paths. I'll show you a little bit. We'll go over a little bit of that a little bit later. You'll still get parallel paths that'll mess up your meter. So the only way to measure resistance is really to disconnect the resistance from the circuit. So that a lot of people in the lab, they'll do stuff like look, this resistance is totally wrong, and it's not. It might be, but a lot of times it's not. So, like I said, there's a whole bunch of these different meters out there. The hold button will like hold your last measurement so that, you can measure something with two hands and just barely get to that button and then it'll stay on the screen. Light, I think is just LED backlight for your display. And then we'll talk about AC when we study AC electricity. Okay. Okay, so now we're going to talk a little bit about circuit analysis. Very, very simple circuit analysis. And we bring back the pump and the water and the pipe. When we pump water through a pipe, the pipe isn't perfect. We lose a little bit of pressure. So if we were to measure the pressure here, it wouldn't be exactly P1. Okay, it would be a little bit less. And then the total pressure, so you can just see conceptually, hopefully, P1 will be equal to the sum of the two pressures. Because right here, if you imagine measuring the pressure right there, is going to be P1. Then you're going to have pressure drop. If we say this is the only place, it's a small pipe and the rest of this is all big and there's not much pressure drop, then all the pressure has to be dropped across these two places. So that's why P1 is equal to P2 plus P3. So if it was 10 psi and maybe we drop 1 psi here, there you'd measure 9 here. Okay. By the way, this is called discharge pressure, and this is suction pressure, if you care about pumps that much. Discharge pressure is always greater than suction pressure. If they're equal, you don't pump anything. So you always have a higher pressure here than you do here, same as with the battery voltage, right? So we'll look at this in terms of a circuit, or its analogous circuit. And basically this shows a resistance here with plus and minus, and then your resistance here, which is actually your nozzle in this case. It's not an exact analogy because, you'll be measuring pressure here, but some of it will be dropping here and through here. But we'll have to use that conceptually. So current comes along here, drops a little bit, or it could be a lot. We don't, it depends on how big this R is. And then we drop the rest here. And then we have V1, the same thing, is equal to VR1 plus VR2. And then I just show you this because you can manipulate this to be V1 minus VR1 minus VR2 is equal to 0. The reason why I show you that is because you can do more complex circuits that way. You can have more resistors hooked up in more places for the current to go, and then you can have them all set up to equal 0, and you can solve them easier. But we're not going to do that now. But using algebra, you can see that the sum of the voltages around the loop, it's called Kirchhoff's current loop. Another famous electrical guy. The sum of the voltages around the loop is equal to 0. Okay, so, and then you can do that with a loop next to it and another loop, up here, and then you can get a bunch of different equations, and then end up solving them. And that you will have to learn in algebra. Okay. Now we're going to get into some parts, some different types of parts. Not too many. We already did a resistor, a battery. We're going to do a capacitor. We'll do an inductor. And then that's it for a little bit. So capacitor has kind of a conceptual analogy. I know I'm great artist here. If we imagine this is a balloon, a flexible rubber balloon, we attach it somehow to our pipe. I drew this X to show you that we're going to cut this off, but let's assume we don't have the X there. We're going to pump this. It's going to end up at the same pressure as the pump. It's going to take water from here, or if we have this closed, it'll fill this up until it exactly gets to the pressure of this. If your balloon doesn't hold that much, then you're going to get wet. But assuming the balloon doesn't pop and it holds this much pressure, it'll fill up and just sit there. Okay, and then once it gets to that pressure, water will keep flowing out here, right? Because this will be the same pressure as this. There'll be no reason for more water to get into there. So conceptually, that kind of hopefully makes some sense. This is analogous to a capacitor. Capacitor holds charge. A lot of times we call it a cap, capacitor or cap. And the symbol is just 2 bars. There's different symbols for it. You can have a curved bar here also. But for us, we're just going to draw 2 parallel plates, because actually that's what it is inside. It could be multiple parallel plates, but really you can just visualize it as 2 parallel plates. And basically what happens is when this switch is closed, this fills up with charge instead of water. Same as this. Okay, when we open this, and we open this switch, this keeps pumping fluid out in this case, and in this case keeps pumping charge out, positive current out. So that's what a capacitor is. It's really just like a balloon that holds charge instead of fluid. Okay. I want to just introduce a symbol here called return or common or ground. So if I look at the next, I'm supposed to have the next circuit. Oh, sorry about that. I should have a circuit here without this wire in. And then I would have a ground symbol here, a ground symbol here, and a ground symbol here. And all it means is it's tied together. So you'll see a lot of drawings with just this symbol spread all over the place. And what that means is they're all hooked together, so it just saves us some drawing time. And makes the drawing a lot neater. Later on, I show that because it helps. So here, all these points are tied together. I could have just drawn a wire across here, but you need to get used to that a little bit, seeing this. And there's also different types of symbols. Like I'll show you some more as we go along. Okay, so that's a capacitor. We added this concept a little bit of a common or a return, and we always need a return. If you have no return, you have no current flow. You could be the return if you touched, if this was off and you touch this and you're touching the ground and this battery's touching the ground, it could always go through you. We don't really want that. 12-volt battery or even a small battery can do a lot of damage to a person if it gets in the right spot. You have a cut on your hand and maybe your foot is standing in water and the battery's also got to somehow ground to water. Could do a lot of damage even though it's low voltage. So batteries are a little dangerous. You always treat a battery with respect. Okay. The next thing I'm going to show you is an inductor, but first I'm going to go over some what I think are cool laws. And then we're going to use these laws to determine how an inductor conceptually works. So Newton's first law. An object in motion tends to stay in motion unless opposed by an outside force. It kind of makes sense, right? I mean, a car's coming at you. I mean, it's gonna, without anybody jamming on the brakes or you stomping it or a wall or something, it's gonna keep moving. So force itself, this is the more interesting one, equals how fast you change momentum. Okay, momentum is mass times velocity. You guys kind of probably understand what momentum is. If you have a heavy ball moving towards you, it has a lot of momentum. If you have a heavy car moving towards you, it has a lot of momentum. Excuse me. A feather coming at you has very low momentum. And when you try to stop that momentum, if you try to stop more momentum, it takes a lot more force, right? Stopping a car is a lot harder than is a lot harder than stopping, let's say, a feather or something very light. So anything that stops very quickly takes a lot of force. So there's an equation that Newton is associated with. Newton F is equal to mass times acceleration. Acceleration can be negative, right? So acceleration, the car can be accelerating. It's when it's leaving a stop sign, and when it's coming to a stop sign, it can be decelerating. So it can be negative. And the force, and then the third law is every force has an equal and opposite force. Okay, it always pushes back. You go to stop that car. If you stop it, you gave it an equal and opposite force to stop it. Okay, so these are really cool laws. There's another law that's really important to life. Energy can neither be created or destroyed. Everybody associates that with Einstein. So if you have water moving along in this pipe and it's energy, you have to dissipate it. It has to go somewhere. Okay. In this case, in the case of water, it's not as easy to see, but it'll go on as friction. It'll heat up. The water will actually heat up. You're putting electricity into this to make the pump work, and this water will heat up. It can't be destroyed. It has to go somewhere. You may not see where it goes, but so with Newton's laws, we can see any water flowing in this pipe. If we were to stop it real quick, and I show a little thing here, R goes to, that's my drawing for infinity. R goes to infinity immediately. Probably, if it, ideally, you would blow this pipe up, or you'd blow your little seal at your faucet, or maybe you'd blow it over here, because the energy has to go somewhere. So it will somehow get out. And this also, conceptually, you guys have washing machines, or go to laundromats. If you look, you'll see the washing machine, assuming it's done right, has a little buffer tube when at the washing machine where the water enters the washing machine. Could also have it inside the washing machine. The commercial ones may have it inside. But at your house, you'll usually see, at your house or apartment, if they install it, they'll usually put this on the outside. And so the water's coming along, and you have something called a solenoid inside that shuts off very quickly. We don't want to spend the money shutting that off slowly with some fancy electronics. We're just going to shut it off with this electric gate, basically. And that water needs someplace to go without busting your pipes. So it goes into this little buffer tube. Hopefully that exists. Otherwise, you know how many times your water comes on and off on your washing machine. It's going to keep pounding this and eventually do something bad. So analogous to that, we have something called an inductor. It basically stores current instead of charge, like a capacitor. So it's a little tough, to think about, but current's flowing just like water in here, and we show it as windings because usually if we want to make an inductor, we wind it a lot of times around something. So when we're passing current through this, if we were to open this quickly, we would get arcs and sparks because it has to go somewhere. And what'll normally happen is it'll actually arc over to this terminal, and you'll see the sparks right in this area here when you do that. But so I'm just saying that the inductors help to hold current. So if you want to hold current for any reason, which you do in electronics and electricity, inductors will hold that for you and give you a little boost when you need it. Another term I'm introducing here is a load. It's the same as a resistor. So this is our load. Could be a motor, could be your car, electronics, could be your computer. They all run off of DC voltages. Oh, I have a little thing, a little example here. If you want to see a spark, I think I already did this in the first class. You can go in the dark and unplug your running vacuum cleaner, but not too often. It's not good for it. The spark can end up back at your electronics in your vacuum cleaner. Although that's AC, we're going to talk about that. AC can be treated a lot of times as mostly as DC, so it'll have the same effect. It'll basically spark. By the time you pull it out, it'll spark. AC current. AC goes from 0 to plus some voltage to negative some voltage, but most likely but every time I've ever pulled out a plug and left when it was powered something, it always made a spark. You could end up pulling it out right at the 0 spot, but it's not likely. And you probably can't pull it out that fast. So no matter what, if you do this, you will get a spark. And it's probably not good for your vacuum cleaner. So that's an inductor, stores current. Same as moving fluid in a pipe. So that's another concept. And then this is, kind of a good way to think about it because it's moving along, and then whoops, off. And then ammo, it goes into this buffer tube. I mean, hopefully there's air up there basically, or some gas up there that compresses. Gas is compressible. Liquid is not. But that's why this works, is because you can compress this air and it'll take a little bit of the energy into the air, turn it into heat energy, most likely, friction. Also some mechanical vibration, which will also turn into heat energy. So, okay, I think I'm going to stop for now, and then we're going to talk about a diode next.
This meeting is being recorded.
Okay, I am getting ready to go over some components that can be used DC and AC electricity, but I'm just going to look at the DC part of them. So the first one is called a diode. That's an interesting part. Conceptually, it's like a flapper valve in a pipe, if you can picture that. So it'll let water go or fluid go one way. And when it goes to go back, the flap will push against the sides of the pipe and stop it from going back. Okay. So conceptually, that's what it is. And this is the symbol for it. It doesn't really have this line. A lot of times people color in the whole thing here, but I have to get these things off the internet for free. So this is the symbol for it. Now it has an anode and a cathode. So fortunately that works out because current goes from A to C, like the alphabet. Okay. So current can only go in this direction, and none, or you can assume none goes back this way. None goes back from C to A, only from A to C. And very little leaks back. I mean, in real life, a little bit leaks back. It's a problem with, well, you guys get equipment, you get little like handheld devices, and you have to pull this little plastic tab out. It's because there's a diode in there, and also your electronics, and so the battery will leak into it. There's a lot of things behave like diodes when they're off, like transistors, and they leak a little bit of current, even when they're off, even when they're in the reverse direction. And so you have to pull the little plastic tab, and then it becomes active. And then when the unit's off, it'll still keep leaking, but at least when they put it on the shelf for 2 years, the battery kind of stays good, although batteries leak on their own also. So this is a diode. Now I drew a capacitor here and a resistor. In the next, no, I thought I put, so what I really want to do is show you if I disconnect this battery. So at first we're charging this capacitor. It's sitting there right at V1 minus whatever this voltage drop here is across this diode. A lot of times they're like 0.5 to 0.7 volts, somewhere in there. It's really not deterministic. Depends on the diode and how much current they have going through them. But so for right now, you just think of it as being a very little drop. So we'll have V1 sitting here. I call it V2 because it's a little different. Now, if I disconnect this battery, this is just like that balloon. We just pumped up the balloon with charge. If we disconnect this battery, charge is going to come flying out of here and into the resistor. For a little while, this charge will discharge. The balloon is filled up. at first, but then it will bleed all the way out. And it'll behave much like a balloon deflating. We have something called an oscilloscope, and you can watch that. It would decay pretty much exactly the way a balloon deflating would decay. Okay, so that's a diode. I'm introducing this, I did this last time too. A return or a common or a ground. I don't know what that R is doing there. It got off to the side here. So I wanted to show you this some more because you'll see this all over if you look at schematics. This is the same circuit as this circuit, okay? So all these points are connected. This is another symbol usually used to signify this to be a symbol for earth ground. In other words, it's hooked to the dirt. And, just like your pipes in your house are hooked to the dirt, basically. But people, they use it for different things. It's also a common. This is usually a signal return. So it's usually in our circuits. Okay, so I'm going to go on to some other, not too much. I'm just going to show you some other parts, another amazing part. And I won't be drawing the line at the bottom. So zoom out here. So now we're going to talk about the most famous part of all, the transistor. Here I show a field effect transistor. I'm actually showing a MOSFET, metal oxide semiconductor field effect transistor. Field effect transistor is a term that covers a whole bunch of the transistors. You guys don't see this little panel here that I see. So a transistor, if you don't need to get really into it, it's like a faucet. It turns on and off. It turns on and off with a very little bit of charge or a little bit of current. So that's why they say they amplify. So we could have a volt here and we could have 100 volts out here. And we could be switching on and off 100 volts. So that's why they call it like transistors amplify. These are what we're watching right now. I mean, there's just billions of them in our computers and everywhere. Before transistors, it was tubes. I actually am old enough to have worked on some tubes. They were still outdated, but in order to do real high power amplifiers and high voltage, you still need tubes, which I'm not going to do anything with. But transistors have just revolutionized all of our electronics. They're just amazing devices. Basically, so I drew an arrow through this. So basically, this is like a power supply or something that generates a different voltage depending on what you want. Okay, so with this transistor the way it is, it's an N FET, N channel FET they call it. When this is 0 and there's 0 voltage across here, the faucet is open. It's an open circuit, so you're going to see no current through here. So this voltage here is going to be the same as this voltage, except for a little tiny drop, through the line and through whatever leaks. Like I said, there is a tiny bit of leakage current through everything that electrical engineers fight a lot, actually. But you don't need to worry about it. Just assume that for this lesson here, it's just V3 is going to be equal to V2 when this is 0. Now, we're going to increase this voltage. And we're going to start turning this faucet on, and a little bit of current's going to start coming through, and a little bit more, and a little bit more, a little bit more, and it's going to go all the way on until V3 becomes zero or close to zero. That's another thing that we fight. It's not exactly zero, but so basically, the water model here works on a transistors. On a transistor, this is what we do in computers. We just turn these on and off. We don't have a slow trickle and then go to a fast one. We just slam them on and off. They use less power that way. If you turn them on and off slowly, they use a lot more power because they kind of turn into a resistor while they're in that mode, while they're turning on and off. I drew a little picture over here. As V1 goes up, if I can zoom out a little bit. As V1 goes up, V3 goes down, right? Until we get very close to zero. Okay. So that's a transistor. There's many different types of them. There's ones that turn on with a voltage that goes to this side. There's many different sizes of them. There's many different types that are a little bit different for different functions. Another one, when I was first in engineering, we only had we had MOSFETs, but not as much. We had bipolar transistors. They still operate exactly the same. They take a little bit more current to get the same amount, as much current as you need out of the what's called the collector on this one. And I don't know why I don't have these named. This is called the gate. This is the source, and this is the drain on a MOSFET. This is the base, this is the collector, and this is the emitter on a NPN. You can look those up. You can study all you like on the internet with transistors. Basically, they turn on and off for all the computer stuff that you're watching right now, the screen you're watching, all the electronics that are running in your house and everything. They have billions of transistors in them that are turning on and off really quick, making zeros and ones. Some of them are used in what we call the active mode, where the faucet's not all the way on. And we use those in amplifiers, like audio. What you're listening to now is driven by transistors that are not all the way on all the time. Excuse me. Now I know why people have water when they talk on the podium. They always have water sitting there next to them, which I don't have. So that's really what a transistor is. To come up with what did this was quite a feat. I think guys at Bell Labs, developed the first NPN in New Jersey. They developed the first NPN, and it was amazing. So, you can study transistors and all these parts, all that you would like on the internet. I'm just trying to give you a conceptual idea of what they are. I thought I should talk a little bit about batteries. We use them so much. They're also, to me, they're as amazing. Not quite as amazing as a transistor, but they are amazing devices. So a battery has a plus and a minus. And basically, a negative flow goes from the negative to the positive, and positive charge equals that out and goes into the negative. It's a chemical reaction inside the battery, and it runs out of uh, the chemical particles that call it the chemical reaction that happens. It's like putting baking soda in vinegar. It bubbles for a while, but then it all settles out, and that's basically what your battery is doing. It's just using up all its chemistry to give all its charge. You can put charge back in by reversing the current in a lot of batteries. Actually, pretty much all batteries you can do that too, but a lot of them will either, some of them like your little alkaline batteries, they'll, if you do that, you can actually recharge an alkaline battery. I mean, I've done it before when I was younger, and they won't hold much charge when you reverse them, but they'll hold a little, and they also can get really hot. So it's a little bit dangerous if you don't know what you're doing. I don't think I blew any up as a kid, though I don't know. Um, so batteries are made up of cells. So if we take a 12-volt battery, they call it 2 volts each for each cell, so that's how they get 12 volts. But when you're charging a battery, you're charging at least at 13.8, 13.6. So you put a battery charger across, and if you hold a DMM, like I showed you, across the battery, when the battery charger's going, it could be even like 14, 14.5 volts. This is for a lead acid battery for your car. There are many types of batteries, like I said. So, but for your car, they're made to be recharged, of course. And your charger is going to run at a fairly higher voltage than 12 volts in order to keep it charged. Now, when you turn the car off, it drops back down to maybe, I don't know, 12 and a half, but it doesn't have to be 12. And if you were to run it without your generator, without your charger, your alternator, your battery would run down fairly quickly. You can actually you actually wreck batteries by letting them discharge too much. Um, the ones you're going to throw out, like your alkaline, we don't care. But lead acid and NiCad and nickel metal hydride and lithium ion, they don't like to be charged all the way out. You suck all the chemistry off of all the plates, and it's hard to get it back on. So you don't want to do that. You want to stop. Most of your equipment will all stop when it gets to a certain safe voltage for the battery, and then tell you we're out of batteries. Your phone will say, I'm out of batteries, but there really is still a charge on your battery. But it doesn't want to go any lower, or the life of the battery will get dramatically shortened. So now lead acid batteries are nice. You can just set them at 13.8 volts or 13.6, anywhere around there, and just leave them. And it's called floating them. And they'll just stay charged and last the longest that way. The other batteries, though, alkaline, alkaline you can't even charge. Lithium ion, NiCad, all the different types, LiPo, all the new batteries that they have. You have to use we say it's an algorithm. You use an algorithm to charge them. So they'll start at maybe a high voltage, like say if it was a 12-volt battery, they might start at like 15 volts for a while. And then they'll have electronics inside that detect the current changing, and they'll say, "Oh, we need to drop down to 13 or something," and then they'll even like pulse. Some chargers will just even pulse just to keep the battery charged, but not continually keep current in it. So batteries are really interesting. Um, uh, they're also, a little bit dangerous. You should treat all batteries with respect. I mean, I don't know. I know I was a dumb kid who took their 9-volt battery and took a 9-volt, one of those ones that are square, and they have the 2 electrodes on the top. Put your tongue to that. Here, kid, put your tongue to that. Yeah, well, I was one of them. They can be, I mean, it burns your tongue badly, uh, depending on how long you do it for. Um, um, but the car batteries have an incredible amount of energy in them. Ask Elon Musk how much energy those lithium ion batteries in the Teslas have. It's an amazing amount. Even your 12-volt battery, they rate them at like 100 amp hours. That means, it doesn't really mean this, but it's rating them they can do 100 amps for an hour. It really can't. It really can do more like 10 amps for 10 hours, but they rate them at 100 amps. So 100 amps is a lot of current. Can burn holes in metal and, pretty thick metal. And so there's a lot of energy in them. You don't want to mess around with batteries all that much. Treat them with respect. The other thing I wanted to bring up was a power supply. It's something you can have on your bench and you can adjust. I think I have just about this one here. They're all kind of made in China now. If you want a cheap one, the Japanese ones are better. Lambda, I think, is still made. Most of these no-name ones are all made in China, though. They act like it too, believe me. So basically, though, these act like a battery, or they want to act like a battery. They take AC, which we're going to start AC current in, and they turn it into DC. Excuse me. So they use a little switching converter to do that. I'm not going to explain that, but basically they can make a lot of noise, and they can mess up if you're a radio person. Can mess up your radio reception and transmission. So that's the cheaper ones. Let me see. So yeah, you can set these up for a different current limit and different output voltage. Turn them on and off, and you can also variable adjust them. So if you have a power supply hooked up like to a resistor, you can sit there and adjust it and then watch the voltage change on it and watch the current in it go. Watch it. If you had a meter hooked up, you could watch the current go up and down. All right, so I'm gonna have to stop this for now. We're gonna go just do something else. I just want to show you something else with DC. I want to show you a simulator. For those of you who want to get more into electronics, it's a really great simulator called Linear LT Spice. Linear Tech, the company, makes this free software. It's a really great simulator. I want to show you that, but I don't have that set up yet. So I will get back. Apologize for the dry throat. Next time I'll try to have water. Okay, I'm going to turn off the recording.
This meeting is being recorded.
Okay, hello. I'm going to finish up my little series on DC electronics by showing you. I'm going to cut this out because I got a cough again. I'm going to start end my little series on DC electricity with a simulation, a demonstration of a simulation. This is LT Spice. If we do about LT Spice, you can download this for free. It's a very good Spice simulator. Spice was the original name of a simulator that the company came out with, Synopsys, and I think it was Synopsys. And this is, I downloaded one recently in the last couple months. They'll always ask you for updates if you want to update or not. But it's a really nice simulator, and you can use a lot of parts, and also a lot of parts they have defined up here. And then they also have a lot of integrated circuits that you can use. You can also import your own integrated circuits from another manufacturer other than Analog Devices. So now LT Spice is not owned by, Linear Tech is now owned by Analog Devices. So they were just bought a couple of years ago. It's 25 now, maybe in 23 they were bought, somewhere around there. So anyway, this is the way it'll come up. You download it and run it. It'll come up looking like this. Go under File and hit New Schematic. It'll give you a blank drawing here. So now we need to figure out what to do with it, like all simulators. So they have a lot of symbols along the top here. Right here is a voltage source, and I showed you this previously in one of the drawings. I kind of drew it like this in Libra Office. So I'm going to just grab that and take it, and it'll keep dropping them. You got to hit escape. So this is a variable voltage source. So we're going to set it to something. We also need a resistor to do anything, right? We can't do much without a resistor with a voltage source. So I'll put one here. You can rotate this up there. It's a little clumsy, this stuff, but I'm going to hit escape when I'm done. All right, now you have to have a ground with LT Spice. It has to have a common point, and they call it ground. All right, so we could just put one down here and then attach. In order to attach, you got to hit this. You're going to have to take a tutorial maybe on this. I just want to give you a brief introduction. If you want to play with this, take a tutorial on it, and they'll do this stuff for you. So I'm just drawing a circuit, very simple circuit with 2 resistors and a voltage source and a ground. And we have to set up everything now, of course. So when I do this, if you just want to do a DC value, you can do that. Let's just make this 12 volts. Series resistance would be basically hiding a resistance in here. We don't need to do that. Each of these resistors need a value. So how about we do 10 and 10? And these are in ohms. Okay. Now, so that's one thing to do that. Now you need to understand that this has to run something over time. Okay. So that's probably a little tough of a concept for somebody just learning to do simulation. So we need to run this somehow, right? It doesn't really do anything just sitting here on the paper. So if you go under simulate here, configure analysis, okay. And there's a bunch of options here because you can do a lot of stuff, but we're just going to leave it where it is. We're just going to do a transient. We're going to put a stop time of, say, 100 milliseconds. And time to start saving data, let's just go 0. Let's just leave the rest. We probably want to start the external supply at 0, okay. And then we're going to hit OK. And it'll put this text here. So it's a transient analysis, 0 to 100 milliseconds, and start the DC voltage at 0. And that's all you really need to do to run this. And then, so if I hit run now, which is this button, or just probably other places too, but it'll split this into 2 screens. It'll leave your circuit down here and put the voltage waveform up here. Now, what do we need to do to see what our results are? If you go down here, you highlight, you make sure you click in this box, and you click, see it turns into a little probe. This will be with respect to ground when I click it. So we're just going to see, because it's just a DC voltage, we're just going to see a straight line going across here. And it's going to be 12 divided by 2 because we have 2 10-ohm resistors here. Okay. So you can do a lot of circuit analysis with this. It doesn't care how many parts you put here. I mean, it'll do it for you. One thing I would like to show you just a little bit more is if I do advanced on this and I do a pulse. So this will be, it's a lot of things to set up here. I apologize, but this You need these things to do more advanced stuff. We're gonna do the initial is 0, be on. We'll go back to 12. The delay, let's just go, I don't know, 10 milliseconds. And type in MS. The rise time, so let's do a rise time of slow, like 30 milliseconds, and a fall time of 30 milliseconds. T on of 30 plus 30. We're only analyzing this over 100 milliseconds. 30 plus 30 is 60 plus 10 is 70. So the on time, we'll just make it 20 milliseconds. And now you can duplicate this. It would be like, say, 200 milliseconds, but we're not plotting it over that amount. So we can do any number of cycles we want because we're only going to see one. Okay. DC values 12 volts. We're going 0 to 12. We're going to start at 0. So let's hit OK. And now it's going to put, oops. This, like I said, it's a little clumsy. You need to look up here. This thing is in my way. I don't know if you guys see this bar, but there's a bar that I'm recording with that's always in my way. I guess I could hide it. So if you want to move something, you have to click one of those up there. Again, take the tutorial. So now this is a pulse. 0 to 12 volts. Delay at 10 milliseconds, so it won't start until here. Take 30 milliseconds to rise. Take 30 milliseconds to fall. Stay on for 20 milliseconds. And then repeat after 200 milliseconds 10 times, but we're not going to get there. Here, I'll show you what happens. So, see, we're ramping up. Start at 10 milliseconds, 20 milliseconds later, we get done. 20 milliseconds, I'm sorry, 30 milliseconds later, we get done. 20 milliseconds later, we get done doing this, and then we start ramping down for 30 milliseconds. So it's a really cool tool. If you guys want to get into electronics more, it's an incredible tool. I think Texas Instruments also has a tool like this. But like I said, you can do amazing things with this. If you look, you got diodes, you got chokes, capacitor, inductors. We call them chokes sometimes. So they choke current, or they stop current from flowing sometimes. They store current, and they also take a while to store it. So it kind of chokes current off. They got diodes, they have voltage supplies, they have now, if I opened components up, they got everything you could imagine for power supplies anyway. I mean, they all even have some digital stuff. If you double click, they'll have, AND gates and OR gates, inverters, counters. So it really is an excellent tool to learn electronics with. I'm not going to really go any further than this. I just wanted to tell you that this exists and it's free. It's got updates all the time. It's a little clumsy, but it doesn't have very many bugs in it. It's really clean, nice piece of software. Okay, so that's it for DC pretty much. Hopefully you got a lot out of this. I'm going to go into AC next. AC is a little tougher to do conceptually. Hopefully I'll be able to help you out with that. And we can turn AC into DC and use all the same tools we use on DC that we use on AC, and I'll show you that. So that'll be next. And for now, sleep well on a concept.
All aliases. Keep the same initial for your signature, remember that's the change. Just an A and M with a squiggle after it, by which student you use. In other words, you can read yours, that page of